So what we're going to do in this lab is investigate LeChatelier's principle. So everything you do in the lab, think of it in terms of equilibrium disturbance, reestablish equilibrium, maybe even more disturbance, reestablish equilibrium. That should be going through your head the whole time we're doing this lab, thinking in those terms. And we covered, yep.
You want to listen to our notebook too?
I'm sorry?
Do you want us to like fill out our notebook before lab with all this in there?
Oh,
Is it too important?
you don't have to. I'd like you to be prepared for the lab, right? No guesswork. I mean, we're not going to, walk into the lab and this is cookbook. I'm not handing you the lab material as you come in the room and then you just step by step. I want you to understand it enough to where, the best way to do it is put it in your lab notebook. But I'm not going to check you to see if you have. Okay, so we've got the first step is we're going to do solubility equilibrium. And it's something as simple as table salt. Table salt can be concentrated to such an effect that it saturates the solution. In other words, if you have sodium chloride saturated in the solution, let's look at this one. Sodium chloride, solid. And then we have, in solution, we have sodium ions, right? And we have chloride ions. And now we're at equilibrium. Right? We may have a little bit of solid in the bottom, and it's being dissolved into these ions. But these ions are at the same time they're returning to solid sodium chloride. We're at equilibrium. So what if I add chloride ions to this solution? What's going to happen? Well, as long as the chloride ions are not accompanied with more sodium ions, then if I only add chlorides, then they're going to react with some of the sodium that's in solution and make more solid. Right? You're going to see precipitate because I've added more of this component. That's a change in concentration. So how would I do that? How about concentrated hydrochloric acid? That has hydrogen ions and chloride ions. But the hydrogen ions are not part of this reaction, so I'm really only adding chloride to this equilibrium. That's how we do it. Okay. What's another possible equilibrium? I mentioned it earlier. Iron and the thiocyanate. We're going to have to form the iron thiocyanate complex first. So we'll add iron 3 chloride to potassium cyanide, potassium thiocyanate. And that gets the thiocyanate and the iron 3 plus ion together. That establishes our equilibrium right then. Now what do? Well, if you add some more iron, what's going to happen? This is going to get redder and redder and redder. What if you add more of this? It's going to get redder and redder. Right? It shifts toward the right. But if there's some way that we can remove one of these, let's go down. See, there's our solubility. Okay, here's our iron. Actually, iron 3 hydroxide is the way we're getting iron 3 there. I thought it was chloride. Oh, no. Okay. All right. It's another solubility problem. Iron hydroxide is insoluble. So you're going to see that drop out of solution when you add iron and hydroxide together. But if you add hydrochloric acid to the system, what's going to happen? What's it going to react with? Well, the hydrogen ions are going to react with the hydroxyls, correct? And what does that produce? Water. So you're going to remove hydroxyls from this system if you add concentrated hydrochloric acid. And that will shift the reaction to the right, which dissolves the iron hydroxide. Okay, that's what you're going to see. How about this one? Let's see. All right, so here we have a situation where we've got the iron 3 thiocyanate in solution, and we want to remove that red color. Right. We've got an equilibrium going on here. Bad. So this is red. So how do we remove that? We have to shift it this way. So we've either got to remove iron 3 plus, or we've got to remove thiocyanate. All right. So if we add some potassium thiocyanate to the solution, that's going in the wrong direction. It's adding these, so it's going to get even redder. So how do we remove some of it? Well, add silver nitrate. These are what's called coupled reactions, because the silver nitrate in aqueous solution completely dissociates into silver ions and nitrate ions. Nitrate's not going to react with any of these. Why? Because all nitrates are soluble. It stays in solution. So iron 3 nitrate is soluble. You're still going to have these aqueous and aqueous. And this is also aqueous, but it's the complex ion. So if this happens, what's possible here? Well, I already said that one with this one doesn't do anything. Right? What are the other possibilities? That one and this one. Right? Those two together. It's a solid. Drops out of solution, which removes it from this environment. Right? So that's gone. If we remove that, what's going to happen to the reaction? It's going to go to the left. And that color is going to disappear. But what's going to replace it? The solid precipitate is not colored. It gets cloudy white because of this. But you lose that color. Okay? Let's see if I can, what are these? Oh, pre-lab questions. Maybe we should look at the pre-labs and I'll let you look at the method. All right, pre-lab 1. What do we mean by stress? And give some examples. In chemical terms, what do we mean by a stress? I didn't use those terms during the lecture, I don't think. But what we mean by a stress is anything that changes the concentration of a reactant or product. It could be a direct involvement, just a simple add or subtract some reactant or product. That's the stress. We could change the temperature. And that shifts the equilibrium based upon endothermic versus exothermic. What it actually does is it changes the K value. But that is based upon whether it's endothermic or exothermic. We can change the pressure. If you change the pressure for a gaseous reaction, then that depends upon how many moles are products and how many moles are reactants. That's a stress, and you need to give some examples. Okay. So I give an example of each one, each type of stress. And how does an equilibrium system behave when a stress is applied? That's straight out of the Lechatelier's principle. Right? What does the system do when it's stressed? Does it just sit there? Well, by definition, a stress affects the equilibrium, so it has to respond. Right? If the stress doesn't affect the equilibrium, it's not a stress. If we call it a stress, but it doesn't affect the equilibrium, then technically it is not a stress. So a stress applied to a system invokes a response from the system that mitigates the stress. It reduces the effect of the stress. Given this gas phase reaction, 2 SO2s, oxygen, and 2 SO3s, suppose that the reaction has already been taking place and the system is now at equilibrium. Okay, that's what this says. If the following changes are made to the system in equilibrium, what effect do these changes have on the system? Shifted to the left or to the right, or not shifted? Now that brings up another point. When you describe things that are happening in this reaction, if you say shifts to the left, shifts to the right, if you don't have a balanced equation in front of you that you apply shift to the left or the right, then those words mean nothing. Shift to the left or right could mean anything without the equation to go with it. So if you're going to say shift to the left, shift to the right, you better have an equation to go with it or it's wrong. Okay? Otherwise, you would say shift to make more product or shift to make more reactant and name them. What are they? I find it easier to include the balanced equation and then say it shifts to the right or the left. Then there's no mistake. All right, so if this is our equation, 2SO2, and that's a gas, plus oxygen. And we're going to make 2 SO3s. Yes. Is that balanced? 2 sulfurs? 1, 2, 6. Yep, that's balanced. Now, what are we going to do for each one of these? Additional oxygen is added to the system. What will happen? If you have this balanced equation in front of you, you can say, adding this shifts to the right. Sulfur trioxide is removed from the system as soon as it forms. If we're subtracting this one, let's see, let me put it down here. Now, if we're subtracting this one, what does that do? It also shifts to the right. Pressure of the system is decreased. All components are gases. If the pressure is decreased, what happens? Well, you've got 1, 2, 3, 1, 3, 2, 3, and 2 over here. If we decrease the pressure, it's going to make more moles of gas. Because it goes from here 2, and this is 3. Now it's going to shift that direction. Correct? A very efficient catalyst is used for the reaction. So the last possibility is the catalyst. Is a catalyst a stress? Right? Is it going to affect the equilibrium position? Yeah, I guess so. What do you think? Okay, we got one for and one against. The against has it. The catalyst has no effect on the equilibrium. It'll just get there quicker. All it does is speeds up the reaction in both directions. Now, this is true for an inorganic catalyst. Organic catalysts are what? Enzymes. Enzymes are a different animal. They behave like catalysts within a narrow range of temperature and other conditions, but they're not exactly like inorganic catalysts. So the catalyst has no effect on equilibrium. In terms of LeChatelier, it does affect the speed with which you arrive at equilibrium. Okay. Let's see, that was number 2. Number 3 is another one. Explain why the solubility of a sparingly soluble salt represents an equilibrium system. So a sparingly soluble salt, what would that be? Well, it doesn't matter really. You have a cation and an anion. Solid, and it's becoming cation in solution and anion in solution. Okay? What would the equilibrium expression for this be? Remember, solid doesn't count. Only these terms count. So the K solubility in this case is simply this one times this one. Okay? So if it's sparingly soluble, that means very small concentrations of these exist. Very small. KSP would be much, much, much less than 1. Okay, now that we have our conditions, let's say, explain why the solubility of a sparingly soluble salt represents an equilibrium system. Well, say you have solid in the bottom of your beaker covered in water. What is it going to do? Well, to establish equilibrium, some of these are going to go into solution. But when equilibrium is established, what conditions exist? You've got things going this way, and you've got things going backwards. So the dissolution rate equals the precipitation rate. That's an equilibrium system. Okay. I say that again. The rate of dissolution this way, the rate of dissolution here equals the rate of precipitation. That's equilibrium. If the forward and reverse rates are equal, we have equilibrium. And that can occur for solubility. It can occur for any of these chemical reactions we described earlier, right, where you actually have reactants becoming something different, products. This is an equilibrium. Solubility is a route toward equilibrium. Phenolphthalein. What's phenolphthalein? Ever heard of that one? It's an indicator. It indicates change in pH. So in acid solutions, phenolphthalein will be clear, no color. In basic solutions, it turns pink. Okay. Phenolphthalein itself is a weak acid, which exhibits equilibrium in solution, right, based upon the hydrogen ion concentration. Right, we're not going to go into that reaction, but the question is, let's see, where is the question? Look it up, either a encyclopedia or an online reference, and find the formula for phenolphthalein. Right, carbon, hydrogen, nitrogen, oxygen, whatever it has in it, sulfur maybe, I don't know. Write the formula. Okay. What's its chemical name? Right? I'm talking about systematic name. It's going to be about that long, and you won't understand a word of it. But write it down anyway. Okay, just to prove that you looked it up. And at what pH does the phenolphthalein change from colorless to pink? Right. It could be a range, actually, a range of pHs. It changes on its way from one to the other. Just write that range in there. Okay? Because we're going to be using that later. That's one of the reasons for it. Wait a minute. Did we use this? We used this in the first semester. We did a titration to determine the molar mass of an acid by titration. Didn't we do that first semester?
I think so.
Yeah. Oh, we're going to do it again, aren't we? For you at Greenbrier.
Yeah.
But we use phenolphthalein as our indicator. Okay, those three items will answer that question. Okay, so those are the pre-labs. These are the results. And in order to get the information to go in these results, what did you observe? And this is the same for every one of them. Observe the effect of adding hydrochloric acid to saturated sodium chloride. What did you actually see? For instance, when you do that to a saturated solution, you see a precipitate. You see more sodium chloride settling to the bottom of your container. Now, the explanation is that equilibrium equation. And which way was it shifted? That's the explanation. The observation is simply, what did you see? The observation should not include an explanation. Just what happened? Okay, that's the same for every one of these. So you'll go through step by step the procedure, which should be back up. Let's see. Here, where does it start? Procedure. So here's where the solubility starts for the sodium chloride, and then you step down through various procedures, and then you have that sheet with places to write your information. Now, what you can do is on the day of the lab, you can just write in what was observed. You don't have to write the explanation right then and there. You can do that later. We want to get the lab finished before the clock strikes 12 and our coach turns back into a pumpkin. Or our horses turn into mice. Cinderella. And I guess by that time, Cinderella has already slopped her driplet. You've heard the Cinderella story told by, what is his name? Archie Campbell. It's called Spoonerisms. He switches the words around. Dropped her slipper. He says she slopped her dripper. He does the whole routine of that stuff. It's a riot. Anyway, that's neither here nor there. So there's your procedure. You need to be able to do that. Now, if you write it in your lab notebook, great. If you don't, be sure that you know what you're doing when you walk in the lab. Okay?
I'm probably just going to read it.